The broadcast is now starting.
Hello, everyone, and welcome to Bird Process Equipment's free educational webinar. I'm Mark Girgenti, the Director of Design Engineering for Bird Process Equipment. I want to welcome everyone for joining us today. With me is Madison Mulqueen. Madison is one of our engineers, and she'll be assisting me throughout the broadcast. She'll be helping to facilitate your questions. And we're going to keep this obviously kind of casual today. We got a lot to cover. We'll talk about that in a minute. But if you have any questions, feel free to drop them into the chat window, and we'll answer them as we go along. And there'll be time also at the end to address any additional questions. Any questions we do not get to during the broadcast, we will send emails out. There will be an email follow-up from this webinar. We're always interested in the feedback from our clients and customers, interested in what you guys like to see for webinars or any additional questions and/or feedback of style. So today we're going to be talking a little bit differently for those of you who have followed our webinar series this year in 2022. And we're going to be talking a little bit more about just a case study in general. So one of the things we often work on when we talk with different groups, engineers, architects, builders, is it's great to understand individual pieces of equipment, be that be pH systems or solvents or lift stations or high purity water systems, but how does everything really kind of come together? People don't often talk about sort of the coordination aspect of all of this. So today what we're going to do is we're going to go a little bit less into the equipment side of things and a little bit more into how you really design these and how they're really implemented into a building structure. And I thought really the best way to do that was to really go through an overall case study. So today we're going to look at an actual case study. This was a building that was built a few years ago. It's a 250,000 square foot unified science center, and it includes teaching laboratories, equipment, shop support, space facilities. And while the project was a LEED Gold building, we're not going to talk about reclaim or LEED today. We certainly can at another point. That's kind of a different conversation. Today we're pretty much focusing on what you would really need or look at if you're going to be setting up a lab space, within this type of a building. All lab spaces, kind of regardless of what they are, their clean room, their biology, their chemistry, their manufacturing, their research, the startup company, startup pharmas, which are very common and kind of popping up. They need a couple of different things. Obviously, they're going to need some kind of a high purity water system, a loop design that carries that water throughout that lab space or building, wastewater treatment, wastewater transfer potentially, and then do you have any solvents based in the actual lab? Solvents can be anything from things like isopropyl alcohols, the acetones, to more like volatile solvents. And while we're not going to specifically talk about solvents today, it is worth noting that they are handled a little bit differently. Solvents obviously need to be collected for use and then destruction off-site. But we can solvent conversation. We do have a webinar on our website for those who are interested in learning a little bit more about solvents. Today we're going to predominantly focus on high purity water and pH and how those two are tied together is part of an overall lab-based design. So when looking at any kind of a high purity water system, if you're starting out on some kind of a lab-based project or case study as we are in this case, there's two things you have to understand. The first is what is the water quality that you need, and the second thing is how much water do you actually need to use or generate in those cases. And water qualities are broken down between a number of different grades. And the most common people typically hear is ASTM, which is broken down to ASTM 1, 2, 3, and 4. And just for clarity's sake, people sometimes talk about like RODI or RO water. RODI water is basically just an acronym, which is used to distinguish between combining the processes of reverse osmosis and deionization into like one term. RODI water doesn't really mean anything. It's broken down between standards such as the ASTM standards, which as you can see here encompass resistivity, pH, TOC, number of different ions between sodium chloride, silicas, bacterias, and these also go to electronics grade waters as well, ASTM E1, E2, E3, E4 as well. There are also the CAP standards. These are not necessarily competing. They're just basically different water standards, and there's CAP 1, 2, 3, and they cover a little bit of a different range of parameters between pH, resistivity, and silica. These used to be called the NCCLS standards at one time, or National Committee for Clinical Laboratory Standards. So different areas of our building are obviously going to need different types of water quality. Excuse me. And When you're talking about things like a college teaching lab or even a pharmaceutical research lab that's located inside of a building, you're typically looking at things like ASTM 2 through 4 CAP standards. And really it depends on what kind of lab structure it is, or biology, if biologics is a bigger concern, if resistivity is a bigger concern. That kind of determines really which water quality that you want to look at for that individual lab space. Humidification systems almost exclusively use RO or just softened water, and that's really just basically that's really utilized so that in that system you don't get any kind of a scaling buildup. Different tools or devices such as autoclaves, glass washers, lab equipment, even semiconductor tools will typically have some kind of an actual parameter associated with them. Most things like autoclaves and glass washers and such use either RO or low grade kind of cap standard water, like cap 2 water for use. Things like semiconductor tools in a lab will typically use much higher water quality standards, which can be achieved also with a local polisher, which we'll talk about here in a couple of minutes. And if you have any clean rooms, that's where you start seeing the ASTM ones, the CAP ones, or even electronics grade water quality standards utilized in them. You understand that when designing a building, you don't necessarily need to have the same water quality in every space. You can design a system to target one, and then you can effectively upgrade it as needed in different areas through point of use polishing. Or if your whole lab space requires it, you can design the system based on that. It really comes down to the economics of the project, and how much money you want to put into the centralized system versus the number of local polishers required for individual use. Talking a little bit about what's involved in any kind of a high purity water system, you have a pretreatment, reverse osmosis, storage tanks, ion exchange if needed, UV, final filters, instrumentation, loop design, and then obviously an EDI. And it's important to understand that when you're looking at an RODI system, you typically break it at a certain point. So if you guys can see my cursor here, really everything between the pretreatment, the RO, and the storage tank is what we refer to as the water generation portion of the system, and everything downstream of it from the recirculation pumps through the loop, we refer to as the recirculation portion. And where that comes into play is when you talk about how much water for a high purity water system, there are two different parameters you need to look at. One is the generation rate, and the other is the distribution rate. Generation rate is the amount of water I need to make up. So when you're talking about a high purity water system, you're feeding X volume. I'm going to generate 1,000 gallons of ASTM2 water a day, or 2,000 gallons, or 3,000 gallons. That's how much water I'm expecting to use in this individual lab space. The distribution rate is through my recirculation loops, I'm going to be sending 20 gallons per minute or 30 gallons per minute through of that 3,000 gallons I'm making up into my loop for actual usage. And those two numbers, while they're linked, are also determined fairly differently. Water generation is really based on what your anticipated usage is. If you have things like different devices or tools, they're going to have some kind of a fixed flow rate. If you have a humidification system, it may be drawing X GPM per minute, and you need to account for that as part of your generation rate for your system. And then, general lab use things like that ultimately will fed down to your pH system, or basically your balance of assuming how much volume per day, and that gives you your generation rate. Generation rates can be expressed in either 8-hour increments or 24-hour increments. From a lot of kind of standard sort of collegiate lab buildings, you're probably looking at 4,500 gallons per day is maybe a rough number that you would utilize. Distribution rates, on the other hand, really vary. They're going to depend on the instantaneous use through the system. They're going to depend on the loop design, which we'll talk about a little bit later, the velocity through the loop. So while it is linked in how much volume you need at the point of use, it's much more based on the loop design and those instantaneous values as opposed to your generation rate, which is based on some total overall usage in your system. And that's really where your storage tank begins to kind of come into play. So this is kind of more of a graphical animation of what I was just explaining. Really everything kind of on this top area here is referred to as the generation rates. And this is where you actually do a majority of your work for high purity water treatment. You have your your filters, carbon, water softening, etc., and then your RO. Your RO is going to be sized for some fixed generation rate, and that feeds your storage tank, which effectively acts as your break between the generation and then your distribution. It allows you to actually do Allows you to basically have a pre-storage volume, one for use, but two also then is basically the point where your circulation loop begins and ends, and you have basically have back pressure regulation at that storage tank. Your water quality in a lot of ways determines kind of what this sort of overall PFD is showing. This is obviously a very simplistic representation. When we get to the actual system we're talking about today, I'll kind of show you a little bit more about how that comes together. But depending on whether you're ASTM1 or ASTM2 water, or cap one, how many UVs, your DI, the DI location, use of EDI, nitrogen blanking, all kinds of different things come into play as part of that overall system design. And like I said, majority of what you do in that space is related, majority of your work is done in your reverse osmosis system. So the RO is really what removes 99% of your total dissolved solids, which are things like your pyrogens, your bacteria, your ions, things like that. And that's really where most of your work is done to actually achieve your different water qualities. We call it the RO in particular because RO is one of the things that's really heavily designed in your system and also has a reject source, something you need to take care of, obviously, from any kind of a building standpoint. When operating an RO system, you do have a reject, which then needs to be collected and then reused as part of either a reclamation system, which is the case in this LEED Gold building, or needs to be sent down, obviously, for waste treatment, even though it's a little more than basically concentrated city water at that point. It's also the point in your system where you really start to look at, generating your water quality. So this is the actual water chemistry data that was used to do this actual design. And one of the things you do in any RO system is you need to do is referred to as an RO projection. So this kind of tells you a lot about some of the different ions. So you have the feed water for sodium, potassium, calcium. You have here, this is the adjusted rate. That's when you actually do the calculation. When you have things in your water chemistry that's not accounted for, you do is referred to as an adjusted rate. And this shows you that you have about 300 TDS coming into your system. Then you calculate a concentrate rate, and your RO reject is 1100. What does that all kind of mean in English? This is really what an RO projection looks like. And I won't go through all the chemistry of this today, but what it's really showing you is kind of what I just described here. You have your sort of initial ion concentrations. You go through, this is your, permeate rate. So as you go through your membranes, this is kind of where you end up with your purified water. And this can be adjusted as a means to basically optimize your high purity water generation. So here, stage 1, stage 2, stage 3 for a total of reduction from here 263 TDS down to 1.24 TDS. That's based on temperature, that's based on the pressure, that's also based on the membrane surface area, which in this case is a 2 by 2 by 1 array. That's why you have stage 1, stage 2, stage 3, two membranes that then feed two membranes that then feed one membrane with their reject. When an RO feeds another RO, that's referred to as a two-pass RO system, and a kind of an oversimplification of the term. And when designing an RO system, one of the things that comes up a lot, and people always ask, is what's the temperature that you should feed the RO at? And one thing that is, RO systems generally operate best from a treatment standpoint at lower temperatures and operate at a higher throughput at higher temperatures. So a lot of people put thermostatic mixing valves to try to heat the water before it goes into the system. I wouldn't highly recommend doing that. As you can see here, the feed temp set at 40 degrees Fahrenheit. I live in the northeastern U.S. And that could be kind of what our water is, definitely in the middle of the winter. And that gives you an excellent permeate rate from a treatment standpoint. It does, however, require increased pressure. And that's really what you're doing in these kind of projections. You're modifying pressures and temperatures, and you're seeing what your different permeate rates come out to actually do your treatment. So this is kind of what goes on sort of behind the scenes when you're talking about the water quality required. Because when you come out of here, you're basically looking at water, which is almost, at this point around like a half a mega ohm. And then from there, you do your additional treatment to where you want to go ASTM, CAP, etc. Oops. I mentioned a little bit earlier about point of use systems. So I've been talking about a lot, sort of showing you the overall graphic of what's referred to as a central plant system, which almost all lab buildings have. And that's where you make up your RO water, you make up your RODIO, your high purity water, whether it's ASTM1 or whatever your overall target water quality is. But if you're designing a facility and you need specific water qualities at specific locations, you utilize what's referred to as a point of use system. And what a point of use system is essentially takes already purified high purity water and brings it to a higher level. This is common when you have, for example, one area that needs like an ASTM type 1 feed or USP feed or however you want to, whatever your water quality is. And these very small units basically take a feed off of your high purity water loop and then allow you to do additional treatments to meet that water quality. And that can be resin, that can be UVs, they can even have like UFs in them. There's different things out there. So this is an option. You can't just take Bay City water to these because Bay City water itself will basically burn through these canisters very quickly. So you need to feed them with a centralized system, but they do have their uses. Really, the trade-off when designing a building like this is if I need 15 of these, at some fixed cost of say $10,000 a piece, should I just be making my centralized system the higher water quality? And that's really where they kind of have to look at, what your individual lab spaces are, what your water quality is, cost to your central system versus overall cost to the project, for doing that. I think now we're going to have our very first poll question. And if these are kind of optional, if you guys want to take a look at them and just kind of highlight some things that we've talked about over the thing, just kind of for fun. And obviously I'll reveal the answer here and give you guys about 30 seconds. Okay, so the question was the water generation rate of a high purity water system is either A, the loop distribution, B, the reverse osmosis or pretreatment rate, C, the final filter, or D, the number of mixed bed canisters. Obviously, as I just talked about, is the reverse osmosis and pretreatment generation rate. And again, that's how much water you're actually going to generate within your actual system. So it kind of transitions right into the slide we have right here, which is when looking at water generation usage, you need to look at what is the actual equipment that you're going to be feeding in your system. So point of use, glass washers, process, autoclaves, filling, process kettles, whatever it ends up being. Then if you have any actual laboratory-based sinks, and then you need to take a diversity factor across your sinks in this equipment, and that's what allows you to really determine your overall generation rate. So we'll do a quick example here. Looking at a loop riser diagram, which I'm going to show you guys in a couple of minutes, we have 80 lab sinks, 5 dishwashers, 4 point of use systems, 5 process machines, and 10 autoclaves. Based on the instantaneous, we have an approximate 2,000 gallons. That's just basically assuming that your actual lab sinks are very low. You're probably talking about a diversity usage between lab sinks of maybe, a couple hundred gallons per day. Things like your dishwashers will be heavy. Process machines in the clean room will be the heaviest users of the water. Every one of those machines will probably be pulling a couple hundred gallons. And again, you typically want to oversize your RO just a little bit in those cases. And 2,000 gallons per day is not considered a very high rate. And that's based on assuming you're looking at an 8 or 12-hour day. That puts you at 3 GPM, about 4,500 gallons over 24 hours or 2,000 gallons over the 8 to 12-hour period for use. And your storage tank will act like a buffer in that arena to allow you to store the water in between uses. RODI water distribution is based on a couple of different things. One, it's based obviously on the amount of water you need at a given time. So if you have these different pieces of equipment out there and you need to feed them at a fixed flow rate, you need to make sure obviously you have sufficient flow in the loop to do that. But you also need to make sure you can maintain sufficient loop turbulence to also allow for that. So very often your distribution rate will be higher than you might actually assume it will be. But a little bit about just kind of loop distribution rates in general. Most of the time, they are made out of a material which is designed for high purity water use. And that's typically used either in polypropylene or PVDF or Kynar, natural polypropylene, or in pharmaceutical applications, it can be like a sanitary stainless steel system. Each one has kind of their pros and cons. Polypropylene is the least expensive of these, like an SDR, like a butter socket fusion system is fairly common when looking at, say, ASTM 2 to 4 water. And PVDF is the only plenum-rated material. It's also utilized quite a bit in semiconductor type applications where you're talking about different water grades. And then you also have natural poly, which is also a lot of times used either in the US, it's more used as a sanitary-based system, which can be utilized for like thermoplastic sanitary, or stainless steel, obviously, which can be used for stainless steel applications. Loops are also broken down between two different styles. You have what's referred to as the serpentine loop or the ladder loop. And what a serpentine loop is it is a loop where the water comes off and it feeds one point of use, you go around and you come back as a single loop. And those are very common in smaller applications. If you have a system that's feeding a single floor or a single lab space or a single industrial facility where you have a couple of different machines, you'll utilize what's referred to as a serpentine loop. Pressure is regulated right at the storage tank for the system, and it basically controls pressure across the entire loop. When you are looking at a multi-story building or very large buildings, very often you have what's referred to as a ladder loop. And in a ladder loop, you come off of your main system, you have a main feed loop, and then off of each one of these loops, you have a small secondary loop. And you control pressure on the main loop back at the storage tank, and you individually control the pressures you can kind of see here off of every one of these sort of secondary loops. This gives you essentially a uniform pressure at each one of the loops, and it also allows you to then change the loop piping between the different levels. So say you only have a very small lab space on this level, but much more lab on that level. These can have different size loops at that point. And that comes obviously the cost when you start sitting with doing a large loop. It could be 4,000 feet or something like that. Changing between a 1.5 inch, say, and a 2 inch line, for example, between different floors is obviously going to be a cost saving also for usage in those cases. And talking about it a little bit, one of the things that comes up quite a bit in loop design is you want to maintain, how much do you want to maintain for friction loss versus loop versus like loop flow. So this is kind of high level friction loss here, and it's not so much a velocity that you're ultimately trying to maintain in the system. What you're really trying to maintain is turbulence in the system. They used to kind of be the old norm that, hey, I want to maintain like 3 to 5 feet per second, knock bacteria. That's not really true per se. What you're really just trying to do when you're doing a loop design calc, taking kind of the friction loss for the piping and the valves, etc., is how much turbulence do I have? So this is kind of what we're looking at here between different pipe sizes. This is all for polypropylene. Whether you have turbulent flow, and then what your actual velocity is, say at different flow rates at different water temperatures. And this is kind of the sweet spot that you want to be in, 60 GPM. And this shows obviously a lot of the different turbulences going on in our different loop. And that's really what you're trying to shoot for when doing those types of calculations.
Hello, everyone. This is Madison here. Mark, I had a question for you following up on these past couple slides. So you just mentioned using pressure, as it's sometimes a misnomer, to knock off bacteria. So I'm imagining with all of the turns in the loop, there has to be some kind of sanitization to keep bacteria down within the loop. So what's required in loop sanitization, and how often is that process required?
Sure. And so one of the things is when you're talking about a high pure water system and you have like the UV lights, that's sanitizing the water. That's not inherently sanitizing your loop. Any water system, obviously, that you're passing water through, and as I mentioned before, turbulence is a concern, but you have weld spots, you have turns, you have valves, whether these ball valves, which are obviously less clean than, say, a diaphragm valve for trapping water. You do end up with bacteria buildup in your loop, which obviously being high purity water, that's one of the major concerns, obviously, in different water qualities is, how much, CFU per mil or 1,000 mils or 100 mils of bacteria is present. And sanitizing a loop is really, the frequency depends really on what your water quality is. And if you have, say, a very high level bacteria spec, you could be sanitizing every day. That's common in semiconductors and pharmaceuticals. They'll sanitize the loop every day. If it's more like a lab-based building, they'll probably sanitize the loop every like 3 to 6 months at that point. When you're doing sanitization, what you're doing is you're injecting a sanitant into your system. And the most common one that I would recommend is ozone in those cases. And what ozone does is it basically is bubbled into your storage tank. You shut off your UV lights, you disconnect any DI bottles in those cases, and you allow the sanitant to run through the system, typically overnight. And the nice thing about ozone thing is it's a gas, is that when it actually reacts, it turns to oxygen and then allows it to basically bubble out of your system. So there's no residual there for removal. If you use things like peroxide base, you need to typically flush the water. You need to typically flush it out of your system, which causes a fair amount of drainage and then also further waste treatment when you have to basically drain those out. But that's really depends on what your water quality ends up being, but it can be anywhere as frequent as every day. In some cases, they have built-in ozonization and very high-end system. They're ozonating the tank constantly, for example, to once a month, once every 3 months, once every 6 months. It should be done at least 2 to 4 times a year, kind of regardless of what your water quality is in those cases.
Great, thanks.
Thanks, Madison. So putting this kind of all together, so we talked about water generation, we talked about the flow rates in our system, the loop designs, the loop law. What does the system actually look like in the end? This is really what the RODI system for this building look like here. And as you kind of can see, you have your pre-treatment, you have your filters, your water softening, your carbon beds. This is your RO system, which had the different arrays I was talking about, where you're feeding one to the other to the other. If we come back, this is your RO reject here, which can then go to lab waste or to drain. You have your mixed beds here on the pre-treatment side for your makeup. In this case, we're targeting ASTM type 2 water, which is obviously only about 1 mega ohm. We go into our storage tank here, which then has our loop return. Coming back, as you can see here, this is our loop return. Those are the pressure regulating valves I was talking about. And this is your distribution here, which is actually relatively simple, where you have go through a UV light, and then this basically has a slipstream back to the DI and then feeds into your actual system. And there's a system there. Systems are actually fairly big, so something to kind of take into account. You have a fair amount of different maintenance and access around these. This is your pre-treatment system here. These are your water softeners. There's your actual RO unit. You have your, I'm sorry, this is your carbon bed. This is your water softener. This is where you have your brine tank. Storage tank, those are your vent filters there. This is your distribution system, controls. You have UV pull-out space. You need access on a fair amount of size for a system like this. This is a fairly common arrangement that you would see that would support like a central lab-based design. Switching gears here at exactly halfway through the presentation. In addition to obviously the process side, when you have any kind of a lab space, you also need to look at pH treatment. And you're utilizing the high purity water in these cases. You're utilizing the different machines, different experiments you have going on. Really, anything that generates or can contaminate water needs to go down, needs to be treated and monitored for use. And what we're really talking about here is, pH, and really anything from household things like juices and bleaches to different chemicals that are utilized, sulfuric acid, sodium hydroxide, all have an impact on the pH that's utilized in your system. And this right here kind of shows sort of the logarithmic nature of pH from basically 0 to 14, 0 to 7 being acidic, 7 to 14 being basic in those cases. And, the waste is really an important part. It's obviously something that's, not so much an afterthought, but something that needs to be taken into consideration when designing any kind of a lab or industrial facility. And, really your permit levels in your area really are going to dictate what level of treatments you need to get to, whether that's going to be 6 to 9, 5 to 11, whether you need more monitoring. But ultimately what you have in your system dictates the sizing of your actual system as well as your flow rates. Every one of those sinks that you're probably utilizing in your lab that you just fed with deionized water needs to then be treated in these cases to allow for additional discharge, like obviously utilized. So it depends very much on the property of so when you have understanding wastewater pH design depends on both what your flow is, how much you have going down the drain between gravity and pump flow, and then also what the nature of your waste is. So a pH system is really broken down. This you can see here kind of a representation of one of them in this case here. And there's a number of things that go into pH system. I'm not going to spend a lot of time today sort of talking about what's kind of going on, but you have treatment tanks, which are based on residency time. Residency time is typically 20 to 30 minutes per treatment tank. Number of stages, single versus two stages, dependent upon the pH characteristics. You have your reagents, acid and 50% sulfuric, 25% sodium dioxide are the most commonly utilized in those cases. And they can, they're double contained. That's a requirement for OSHA. How much you can actually store, that kind of depends a little bit on where your location is. And then you have some form of an effluent monitoring in those cases, which is obviously where you monitor before the city or your municipality how much waste you're actually going, how much waste you're putting down. In a lot of cases, as a flow meter, and what your relative concentration of your pH is going down the drain.
So, Mark, I had another question for you at this point. So I see in this graphic that we have the smaller reagent tanks offboard of the skid as the holding and treatment tanks. So I was wondering, is there any benefit to having those reagent drums on board versus off board, and does it depend on the system? What are those qualities that go into that decision?
Yeah, thank you, Madison. A lot of those are kind of like dependent on the person, obviously, and the actual client in general. So obviously you need two reagent chemicals, whether it be acid, sulfuric acid or sodium hydroxide, and there are really pros and cons to both, and a lot of that comes down to chemical handling. So as you pointed out here, these are actually double contained fixed tanks, which obviously need to be filled either from a tote or a drum. And really the other option is to just bring a drum up to it and then you have your actual draw lines for your chemical go into them. Really, it depends. In a lot of cases, if you have the equipment and you have the drum handling capabilities, having a drum is good, but you do have to remember that no matter which way you do it, you are handling chemicals. If you're pumping it into a reagent tank, you have a pump down that has to go in and draw out. If you're going to be changing out drums, you're going to be pulling out suction wands that have been immersed in the chemical and putting them into a new one. Me personally, I like to have onboard tanks because I think it's easier to have a fixed system where you're not actually touching the metering pumps or any of that equipment. You're simply just opening up a fill cap and then just filling them. Some people, they'll like to do drum exchanges, and they use drums in other areas of the facility, and they bring them in like that. So it really depends on, owner preference at that point. Regardless, if you use drums, you can't just put them there. They still have to be double contained. They have to go on some kind of either a spill pallet or a cabinet. There's a fair amount of handling when you are swapping out drums. So my experience is personal ones who use tanks, but there are pros and cons to really using both of those.
Okay, great, thanks.
So when talking about pH system design, as I just mentioned, there really are two things. You need to have, you're talking about flow and the nature of the waste. And flow is a little bit tricky because flow, obviously, from a pH system, now you're talking, we're talking about high purity water systems before. We had machines, we had sinks, we had a lot of different things we could look at and say, okay, this is how much water is going to be used in different portions of your building. Talking about pH system now we're looking at everything going down the drain. And everything going down the drain is either going to have to go down, in whenever it's used. It's going to be, depending on what those drain inverts are. Is it possible to even direct this all to a system, or does some of it have to be pumped in those cases? Those drains are going to be below ground. So you end up with kind of a mix of gravity as well as pump flow potentially being utilized when doing the pH system design. So there are times when gravity is not possible. And as kind of a disclaimer, as much as it's good to have a system, have a pump system feed any kind of a pH system, from a pH design point, it's not really what you want in your system because pumps are obviously a point of failure. So once you have to introduce another piece of equipment like a lift station upstream of a pH system, you've introduced a point which can actually cause failure in your system. So if you can go by gravity all the time, that's great. The benefit of having a pump system is that you have a known fixed flow rate now, which then allows you to pump into your system. And very often it ends up being a combination of these two different features where one is a pump-based system and the other is a gravity. Or say things like on the first floor, for example, that riser diagram I showed you guys earlier, you can go to the lift station from the first floor and then all the subsequent floors then flow by gravity down. The other case where you see lift stations utilized often is when you have to do an addition. If you're adding an additional lab spacing that's not tied into the base drainage, or the drainage line is too far away, putting in a smaller simplex design lift station that allows you to pump from these individual lab sinks into into either another lift station or then into your pH system from there. The difference with lift stations is most of them, and a lot of them end up being duplex for that reason, is because obviously if your lift station where you have these cases fails, you're just going to back up your drains in those cases. It's also the reason why lift stations do not apply diversity. So when you're talking about gravity flow to a system very often, you're talking about 20% diversity or 30% diversity. But when talking about a lift station or pump-based system, you're always talking about applying no diversity because you have to be able to always pump down your system. And typically you take whatever the maximum flow rate is to it plus 10% to allow you to always do pump down in those cases. And here we're going to have our second poll question. This is going to cover pH systems. Again, take a few seconds to open it, and then we'll kind of go through it here in about 30 seconds. All right, so the poll question was, when doing lift station design, what diversity factor is applied? And we just kind of went through that. When you're talking about a pH style system, your diversity factor tends to be 20 to 30%. When you're talking about a lift station, there's no diversity because you always have to assume that any kind of gravity system is obviously designed for gravity. And a lift station, obviously being a pump-based system, needs to actually operate. The only place it can go is actually into the lift station, so you have to apply no diversity factor to it. And we do a system sizing example here in a few minutes. We'll kind of go through that and sort of show the differences between pumped and flow and how they overall contribute to the flow rate within our actual building. But first, as I mentioned, in addition to understanding the flow through the flow rate as part of the pH system design, the other ones was referred to as the nature of the waste. And that's where we talked about the pH scale here a few moments ago, talking about pH ranges going from, say, really from 2 to 12 pH. That's pretty standard waste that you typically see going into a pH system. That's going to have some trace levels of chemistry in it. That's going to be washed down from cleaning detergents, CIP cleaners, things like that. And when you start talking about waste stream, it's going to go out of those ranges of pH 1, pH 13 and above. That's considered relatively strong waste. And all of that kind of needs to be taken into account. But in kind of a real world setting, how do you really determine what that pH is? It's a little bit tricky, honestly. You obviously know what chemicals are being utilized in different lab spaces. They have to keep a list, there of every chemical being utilized. And I've seen these lists and they end up being 500 different chemicals, half of which are dyes and things like that, which have no real impact. And then just lists a bunch of acids and bases. It doesn't really tell you what's going on in the lab. What you kind of want to look at is what type of a lab is. Is it biology, chemistry, clean room? Is it kind of a red flag for stronger waste streams? Animal handling probably implies more solids being utilized down the drain. Manufacturing has its own set of challenges. If it's like aerospace or things like that, they may have a lot of like plating type kind of chemistries. Pharmaceuticals can be a lot of CIP, or maybe we need effluent decontamination prior to go down to the system. Kind of where you are and what that needs. That tells you more than looking at a chemical list. And then the other big one, of course, is the presence of deionized water. As we just talked about, almost all lab spaces use these kind of two in concert. You have treated water or high purity water system that feeds your lab, and now that water goes down the drain. And one of the processes utilized in high purity water is the RO, and water softening takes out all the alkalinity in your system. And what alkalinity does is it basically acts as a buffer. So if you have a very high concentration of high purity water, and high is a relative term, I understand that, but if you're dumping, say, all USP or Wi-Fi water down the drain effectively, this is a concern. If you're using some of this in a lab and washing it down with a bunch of other stuff, it's not a concern at all. So it's a little bit subjective in that case, but when you do have a high presence of deionized water, you do need to account for that as part of your pH treatment design. And otherwise, what ends up happening is as you do the treatment, you end up with this kind of like oscillatory pH curve here. That's because your reagent.
Hello, everyone. We are experiencing some technical difficulties right now. We're trying to get Mark his audio back online, so just hold on for a couple minutes and we'll be back up. Thank you.
Thank you, Madison. I do apologize for that. There was a little bit of audio issues there. I hope everyone can hear me now. And as I was just explaining a little bit of alkalinity in this case, alkalinity is a major. Alkalinity is a major concern when doing when you have a high presence of deionized water in your system. And where it's really utilized is, you have basically another reagent, which is basically a buffer. What you're trying to do here is when you don't have the presence of alkalinity, you don't have any sufficient alkalinity in your system, then you end up with kind of this oscillatory curve here. And you add another reagent, which is a buffer in those cases, then allow you to do a nice linear treatment in those cases. And again, we're talking about the presence of high purity water. What we're talking about is a significant portion of high purity water, not a little bit of deionized water like you may have in some lab-based spaces, but you're dumping a lot of it down the drain in concert with just kind of like raw waste at that point. You do need to take into account this alkalinity concern in those cases. So let's put this all together. So how do you really look at and size a pH system, looking at different, things like gravity coming into it and pump flow? Well, the first thing you're going to do is you're going to develop that flow profile. So lab sinks 1 GPM, cup sinks, fume hoods, and then you can use your diversity factor of 20 to 30%. Cage washers and autoclaves and dishwashers are assumed to operate at their max flow. Process that generates constant issues need to be added into the maximum flow, and then all lift stations are sized for the maximum, and the lift station systems at 100% of their maximum flow.
So, Mark, at this point, I have another question for you. So, you were discussing systems, when they're fed by gravity and they don't have to be pumped up, or sometimes they do have to be pumped up with the lift station. And sometimes you can assume that the waste is always going, up from the point where it's being pumped. But what about if the effluent is, going below grade from the building or under the building? How do you account for that in system design?
Thanks, Matt. That's actually a good question because, we talked a little bit, as you mentioned before, about when parts of the building, obviously, from the drainage go underground. And one of the questions that comes up a lot is, can you actually put a pH system in the ground? And the answer is sort of. And what I mean by that is, ideally, you don't want to really put a pH system in like a vault. pH systems are never direct buried per se, regardless. You really don't want to do that. This gets into a lot of issues as far as tank design and different types of tanks which are designed for acid and base when they're actually in the ground like that, buried. You can put a pH system in a vault. You basically have an access to it, and that's done fairly commonly. You don't want to put reagent systems in vaults because now you have the additional issues of having to bring reagents down into like a confined space area at that point, because everything down is going to basically become confined space. So then you really want to only have top access, which is nice. pH systems generally do have all top access, where they're going to have their pH probes or mixers all located on top. Sampling from the U-trap becomes a bit trickier in those cases too. So there's kind of a trade-off between doing that and just putting in a larger lift station there and then pumping it up to a ground level pH system. That would be my recommendation most of the time. Keep the pH system as one unit and simply have a larger lift station down there to basically transfer the entire facility waste up. but you can put just the treatment tanks in a vault and then allow everything else to basically sit above that pit. And then just bear in mind that when you do have to go in there, there's going to be confined space at that point. So that does come up quite a bit actually in pH system design.
Interesting. Thank you.
So talking about our case study here, we have 80 lab sinks just like we had previously in our rotary system, 5 glass washers, 10 autoclaves. So first of all, the profile pictures that need to be pumped. So based on our riser diagram, we have 20 lab sinks and 2 glass washers that need to actually be pumped. So the lab sinks at 1 GPM times 20 lab sinks is 20 gallons per minute. 2 cage washers operating at 16 GPM total. We need a total pump flow of 36 GPM. Sizing our lift station in this case, you typically want to obviously size it for 10% up to ensure pump down, and you generally size a lift station for pump short cycling at about 3 to 5 minutes of residency time or no more than 10 pump starts per hour. So in this case, 36 GPM, 40 GPM total size is 120 gallons per minute based on 3-minute residency time. And we made a system duplex for redundancy. For our gravity case, you guys kind of see how the difference kind of compares. 60 lab sinks, 3 glass washers and 10 autoclaves, 60 GPM calculated flow with a 20% diversity factor. It's only 12 GPM. You're going to more than likely see it at any given time. Same applies to the glass washers, autoclaves. So we end up with a total gravity flow rate of only 38 GPM versus the 36 pump, because obviously the pump is sized for 100% of the flow rate in those cases. So to develop the flow profile, we have 40 GPM pumps plus 38 GPM gravity. We end up with a 78 GPM total flow rate for our system. And this is what we'll utilize to then do our actual calculations for our different stages and sizing. Looking at the pH range, so this is going to be determined from the characteristics here. As I mentioned earlier, strong acids are kind of 0 to 2, strong bases are kind of 12 to 13 to 14. This is kind of the normal treatment range. And we're going to likely fall within this range, kind of 3 to 12 in these cases here, but we do have some high purity water presence in the system. So based on all of that, I'd recommend a 2-stage system. Based on 78 GPM, at 20-minute residency time, you'd have 1,560 gallons of total for 20-minute residency time, so it'd be 2 800-gallon treatment tanks. And looking at it schematically, 2 800-gallon treatment tanks, you have dual acid and caustic injection. This is your bicarbonate injection for your to account for the alkalinity addition for your high purity water. As you can see, these systems can get pretty big, obviously. So something definitely to account for at over 200 inches and 7 feet in wide with access. It's not uncommon to split these systems up if needed, especially for access. They split them here, have one tank this way with the panel, one tank this way with the reagents on there. Or the tanks can obviously ship loose in those cases. In this case, they can just knock down a wall and bring the system in. And then from a P&ID standpoint, we have our 2 treatment tanks, our lift station flow and our gravity and fluent flow. We have our bicarbonate addition, we have our acid and base addition, and then we have our final effluent of flow and pH in those cases. And that's it. I mean, that's kind of sort of a simple rendition of kind of how you go through any real life scenario and kind of do the sizing for both a high purity water system as well as a pH system, which will then be utilized for a given lab space. Obviously, there's a lot of different nuances to these that can come into play: access, different chemistries, different loop designs. But this kind of gives you still kind of follow a lot of the same steps overall in these types of systems, where you go through and you develop your flow profiles, your water generation rates, your water quality requirements, your waste profile, your waste generation rates. And this is really what kind of goes on when we're really doing this kind of design, kind of behind the scenes for specification and then for building your actual building. I want to thank you guys for coming today. We do have a few minutes here left, for any questions. There will be some more upcoming events, throughout the year and starting into early next year. I can't believe I'm already saying that, but it is middle of September at that point, so please feel free to check back. We will be sending out a survey following this as well to get your guys' feedback, and this recording will be available online for viewing as well for anybody who wishes to review it. And at this point, I'll open up to any more additional questions.
So Mark, it does look like we had a question from pretty early on in the presentation. I'm not exactly sure which slide it was from, but it was asking how the safety factor was determined within one of the earlier system designs. Let me see if I can go back and see which slide. I believe it was for the case-specific roadie water system that you had first overviewed on slide 13.
Sure. So when talking about like safety considerations, so when you're talking about, assuming you're talking about sizing safety considerations in those cases, and you know, so one of the things to obviously look at is when talking about generation rates versus flow rates, is for the generation rates, you know, you can look at number of uses per day. So say each unit is 15 to 20 gallons, and it has then a usage rate of say 10 or 15 times per day. So you know that's going to be 360 gallons. You then have your sink usage of say 1 gallon or 2 gallons per hour per day, et cetera. So that's going to give you some value in those cases, and that's, you know, that number that I would typically multiply that by 2. Basically, in those cases, that gives you room for future expansion of lab space, changing of equipment, things like that. That's then utilized. You may only really have 1,000 gallons per day, but we'll size a system for 3,000 or 2,000 gallons per day of actual water makeup. The storage tank is a little bit trickier to size. Storage tank is sized based on volume, but it's also sized based on water quality. So the higher the water quality, typically the smaller the storage volume, because that is a space where you can then get some level of water degradation in your system. And when you're sizing it for the loop flow rate in those cases, you know, you are going to need usually quite a bit more. You also have to have a return loop. So you have to keep the water turbulent at all times. So if you are using 30 gallons a minute, you're probably going to size your distribution rate for 65 gallons a minute. So that if you do have a worst case where you're draining your loop out, you still have 35 to 40 GPM flow to allow you to maintain that turbulence in your system. That's why loop flow rates can often seem kind of high relative to the generation rate. And that's because you're trying to basically maintain that turbulency in your system at that point. Hope that was the question. If not, if whoever that person was, feel free to email me directly and we can certainly discuss it in more detail.
It is one of our own, so I think it would be easy to talk about.
All right. All right. Well, I want to thank everyone for joining us today. If you have any more additional questions, feel free to reach out. I hope you all enjoyed this presentation. Again, it will be available for viewing here in the next couple of days, and we're always welcome your feedback. Thank you, and stay tuned for additional webinars to come in the future. Have a good afternoon.